today we shall discuss Lyman series transition rates lifetimes. Hydrogen atom, we found the energy levels in earlier discussions. This is the ground state, and energy levels go as this we found, so that you have many energy levels. Let us consider the ground state energy level equals 1. L goes from 0, 1 to n minus 1. So for the ground state, L equals 0. For the next excited state, we have n equals 2, L equals 0. And then we have n equals 2, L equals 1. And there are 3m values for this thing, plus 1, 0, minus 1. And there are other n states. So these states, when excited, some of them, not all of them, some of them emit a photon, and the atom goes back to its ground state. So this will be, for example, one mode of de-excitation. And there will be other states with L equals 1. We shall discuss that. So these transitions from n larger than or equal to 2, in this case n equals 2, here it's 3 and 4, etc. They radiate with the L equals 1, from L equals 1 level, a photon, and atom is de-excited to n equals 1, L equals 0 ground state. These transitions are called Lyman transitions. Theodore Lyman was a physics professor at Harvard University. He lived something 1875 to 19. These are not the exact dates, but this is roughly the time. And he was a professor at Harvard, and his work, of course, was important. And Harvard named the laboratory Lyman Laboratory of Physics, honoring his name. Let us look at the photon wavelengths. For example, h bar omega, that's the transition. This is 2 pi f, and this is h bar 2 pi c over lambda, and lambda would be then h bar 2 pi h bar c over this energy, which is h bar omega. So the wavelength for lambda, the wavelength for transition from n equals 2, n equals 1. By the way, these are named by Greek letters, so this is called the Lyman Alpha. The next one, n equals 3, is called Lyman Beta. So it goes like this. Lyman Alpha, that's n equals 2 to 1. This is 2 pi. The energy difference between the first and the second. So this is 13.6. This is 3.4. So 10.2 is the difference. Divided by 10.2 electron volt. And h bar c is, roughly speaking, 2000 electron volt. We are just trying to make an order of magnitude calculation, not an exact one. So this cancels. So this is, let's say that this is 10, and this is 4, 315 times 4. This is like roughly 1260 angstroms. So this is from the next level. The series limit is when n goes to infinity, namely you are almost at here. So lambda n goes to n like infinity, going to n equals 1. This, we are looking for the series limit. This is 2 pi 2000 electron volt angstrom divided by 13.6 electron volts. So so 4, this is 3.4. So 314 divided by 3.4 times 1000 lambda. So this is less than 1, and so let's divide. So it is above 900 angstroms. Okay. So if you make an exact calculation, it is something like 911 angstroms. And this is the exact one is, I believe, it doesn't matter. So the important thing is that these numbers are all in the ultraviolet. So all the transitions of the Lyman series from the least energetic one to the most energetic one, they are all in the ultraviolet. So they are not in the optical region, they are in the energetic, more energetic photons, and they are in the ultraviolet. All right. Now it turns out that these transitions are caused by the electric dipole transitions. And let me just set up the structure of the electric dipole transition. So I'm erasing this. All right. The dipole operator, D, is a vector operator, E and R. This is the position of the electron. For heavier atoms, we would make a sum over all the electrons, but hydrogen is the simplest. We have only one electron. And this dipole operator causes a transition from state with principal quantum number n, orbital angular quantum number L, and orbital magnetic quantum number m, d, to the ground state, which is 1, 0, 0. And let us look at the structure of this matrix element. So we will look into the structure of it. Let me write the R operator. This is equal to dr R and L, the radial part, times the angular part. The radial parts, as we computed before, were real. So that's the spherical harmonic. Then we have minus ER, that's the dipole. And for this one, R10, Y00. Since we have spherical harmonics, it is better to decompose now R like this. R, by definition, it is XX plus YY plus ZZ. And I will write this part like this. these are unit vectors in the x direction, in the y direction. And these are just the coordinate values, x, y, and z. Let's check that this agrees with that. This is xx over root 2 times root 2, xx over 2, xx over 2. Okay, so it's xx. Y's are the same, minus I plus I, so it is. Let's see that, for example, x, y disappears. We have I, x, vector y, and minus I, x, vector y, so they cancel. So this is correct. Now let me denote these as r minus epsilon plus unit vector. This is a unit vector. This is r plus epsilon minus unit vector. And let's call it epsilon 0, r 0, epsilon 0. Epsilon vectors, epsilon sigma, where sigma can be plus 1, 0, or minus 1. This is the plus, this is the minus, this is the 0. They have this property dot epsilon sigma prime. That's a Kronecker delta. And r minus, which is x minus iy over root 2, that is 4 pi over 3 r y1 minus 1, r plus, which is x plus iy over root 2, that's equal to 4 minus root 4 pi over 3 r y1 1, and r0, which is just z, and this is 4 pi over 3 r y0 0. So if you put this expression into here, we see that there's a radial integral and there's an angular integral. So let's keep in mind, and I will write to the line above. I will not erase much, it's just this much. And NLM D100 equals, I have minus E from the D, minus E, and then everybody has a root 4 pi over 3, so I take that out. Root 4 pi over 3. Every term here has an r, so I can take r out from the angular integral. So the angular integral is this, the omega y l m star. Then y1 minus 1 epsilon plus minus y1 epsilon minus here plus y1 0. This is not y1 0. plus y1 0 epsilon 0 multiplied by y0 0. I use them so I can erase this part quickly. Z is y1 0. Okay, it's cosine theta. It's r cosine theta. I'm erasing. Now the radial integral from 0 to infinity dr r square. Then I have r and l. Then I have the r coming from the dipole operator, r1 0 equals. Now we can do some of the integrals very fast because this is only a constant. This is 1 over root 4 pi. So this cancels the 4 pi here. And another thing is that the orthonormality of the spherical harmonics. Spherical harmonics are just like the unit vectors, but in the angle space. So y l m star, y l prime m prime, over the angles is delta l l prime delta m m prime. Therefore, we can write the angle integrals. We can do the angle integrals very fast. And let us, for short, denote this by a shorthand notation, NLR10. So the result of this integration is minus e over root 3. Then here m, since this is fixed, m has perhaps it's delta m minus 1 epsilon plus minus delta m 1 epsilon minus plus delta m 0 epsilon 0 times this thing, NL R10. But there is one important thing, L prime, that means L has to be equal to 1. So let me just put here minus E delta L1. So L has to be 1. Why? Because the ground state has no angular momentum. This has 1 angular momentum. So this has to match. Therefore, I can replace L by 1 and 1 R 1 0. Let me write it again cleanly. Same thing. Minus E over root 3 delta L1. Then I have this delta m minus 1 epsilon plus minus delta m1 epsilon minus plus delta m0 epsilon 0 times n1 r1 0. So this is the this. Perhaps I erase the intermediate steps here. Let me not write this again here. So this is equal to that. You may notice a few things. This is a probability amplitude that this state via dipole operator will decay into 1 0 0 state. So this is the probability amplitude. The probability, of course, will be the square. And the square can easily be taken because when you multiply it by its complex conjugate and dot it, these are orthogonal vectors and of unit magnitude. They are orthonormal. So NLM d 1, 0, 0 absolute square will be E square over 3 delta L1. All these things will minus 1 plus delta M1 plus delta M0 times N1 R1 0. This is real, so it's square. What can we say from this? It says that this is the coupling strength of any NLM to the ground state via the dipole operator. It says that since the dipole operator is a vector operator, namely L orbital quantum number is 1, it can connect only with L equals 1 states. And furthermore, the strength of every M value, whether it be minus 1, plus 1, or 0, are the same. So they decay at the same rate. This is our result. Of course, we need to compute this matrix element. This will be our next step. Now we will compute we did the angular integral. Now we are doing the radial integral. And that's where the coupling strength lies. The other one is just geometry. But this one is the dynamical coupling. R N1. For this case, N2. And R. And the ground state, which is N equals 1, L equals 0. So what are those wave functions, radial functions? R and L is N and L. R to the L, e to the minus R over N, N being the principal quantum number, then L 12 plus 1, N minus L minus 1, to R over N. This is the associated Laguerre polynomials that we studied before. And what is the normalization coefficient? This we had calculated before in the earlier videos. This is N over 2, 12 plus 3, 2N, N plus L factorial divided by N minus 1 factorial. So let us find these functions. So this is the general formula. Let's begin with that one. N1 equals 1 over square root N over 2. L is now 1, so it is 2 times 1 is 2. So it is 5, 2N, N plus 1 factorial divided by N minus 1, N minus 2 factorial. N minus 2 factorial. This is equal to, we have 2 to the 5, cancels with 2, 2 to the 4, square root is 2 to the square, so we have 4 upstairs. Then I have n to the 5 and n to the 6, square root n to the 6. And if we open up this factorial, this is n plus 1 and n minus 1 times n minus 2 factorial. So this is cancelled. I have n plus 1, n minus 1. So it is 4. So this is 7. 4 over n to the 7/2 square root of n plus 1 n minus 1. So that Rn1 is nn1. I don't need to write it again. I have it here. Times L is 1. I'm looking at here. R e to the minus r over n. L 3. This is 1. N minus 1 minus 1. So it is n minus 2. 2r over n. So this is the function that goes in here. Let's do the same thing for R1 0. First n1 0, the normalization constant. We are here. N is 1, L is equal to 0. So this is 0. This is 1 over 2 cubed. 1 over 2 cubed times 2, n is 1. This is 1 plus 0 factorial. 1 factorial is 1. And this is 1 minus 0 minus 1. 1 minus 1, 0 factorial, which is also 1. So this is simply 2. Therefore, R10 is equal to 2. Now let's look at here. R to the 0, that's 1. N is 1, so I have e to the minus r. Then I have L. L is 0. L 1. This is 0. 1 minus 0 minus 1. This is 0. 2r. But we did before, with 0 this is 1. So this is just 1. So it is equal to 2 e to the minus r. So let me just write here. R10 is equal to 2 e to the minus r. Let me just write the normalization coefficients and erase this part of the blackboard. N1 is equal to 4 over n 7/2 root n plus 1 n minus 1, and n10 is simply 2. Okay, so I will erase all this. We don't need these anymore. Okay, all right, we erase the blackboard so that we have place to work. So let me write it like this: n1 r10, where I mean n1 is this, and let me divide, not to take up space, with n1 and n10 without writing them. We know what they are. This is 0 to infinity dr. Now how many r's we have? There is the r square from the volume element, r coming from the dipole operator, r cubed, and there is another r from this state. So that is r to the 4. R to the 4 e to the minus r over n coming from here. Then there is another e to the minus r coming from here. E to the minus r. And then L3 n minus 2 2r over n. This is easy. E r n plus 1 over n. You see, the easiest thing is to change the variable from r to 2r over n. So let's do it. X equals 2r over n. That means r equals n over 2x. And this is equal to r to the fourth, and there is an dr, n over 2 to the 5, 0 to infinity, dx, x to the 4. Now, e to the minus, instead of r, we write n over 2x, n over 2x times n1 plus n times L3 n minus 2 x. So these n's go. Now we have to take this integral for all n larger than or equal to 2. So to do that, of course, one should find an easier way, and we can use the generating function that we have studied before. So instead of this integral, let us consider this integral. I equals 0 to infinity dx x to the 4 e to the minus x n plus 1 over 2 times g3 ux. This generates all the L upstairs, 3 associated Lagrange. What is that? This is equal to sum over k from 0 to infinity u to the k L3 kx. Therefore, this integral becomes sum over k uk jk and we need this j n minus 2. So we need k, look for the coefficient, look for the coefficient of u to the n minus 2. This is what we will do. So that means we will take the integral, expand it in u, and then look at the coefficient of u n minus 2. That will be j n minus 2, and we will just take it and plug it in here. The advantage is that the closed form of g is simple, so that we can take the integral exactly. This is equals 1 minus u. This is alpha plus 1 if this was alpha. So it is 4 e to the minus x u over 1 minus u. So we just put it in here, take the integral, expand it, look at the coefficient jk, and plug that thing in here. So that's what we begin. I equals 1 minus u to the 4, 0 to infinity dx x to the 4, e to the x. I have an exponential here and another exponential there. So it is n plus 1 over 2 minus u over 1 minus u. That's it. What is this square parenthesis? This is, I'm multiplying this and that, n minus nu plus 1 minus u This is plus. Minus, because I have a minus, so it is this, all right, plus 2u. Divided by 2 times 1 minus u. Let's see what it is, n plus 1. Then, since n is, here I have a plus u, here I have a minus n. Since n is larger than or equal to 2, let me just take it u, parenthesis, n minus 1 over 2, 1 minus u. Let me call this A. So this is e to the minus ax. Now you see the integral is very easy. Just change the variable once more to y equals ax. X is equal to y over a. So this is equal to 1 over 1 minus u 4 a to the 5th, but a is it's 1 over a to the 5th. So this is upstairs, this is downstairs. So it is 2 to the 5th, 1 minus u to the 5th, divided by n plus 1 minus u n minus 1 to the 5th times 0 to infinity dy y to the 4 e to the minus y. And this integral is gamma 5 or 4 factorial. So this is integral is equal to 4 factorial. Now I will erase something. Before erasing, let me just shorten it here, and then we'll clean the blackboard. This is n over 2 to the 5 j n minus 2. And let me write here, I is equal to k u to the k jk, and we will look for that k which is equal to n minus 2. I am erasing the rest because I will write this here and then go on with the calculation. So some simplification here, this cancels, so 1 power is left. So this is equal to 2 to the 5, 1 minus u. Let me times 4 factorial. 4 factorial is here. All right. Now let me write this denominator in this fashion. It is n plus 1 to the 5, 1 minus u, n minus 1 over n plus 1, 5. You see why I'm doing it? Because I want to expand this. Okay. And this is 4 factorial 2 to the 5, 1 minus u, divided by n plus 1 to the 5. Now sum over k from 0 to infinity. 5, because we are expanding and the power is 5. 5 plus k minus 1 and k, that's the binomial, uk times n minus 1, n plus 1. N minus 1, n plus 1 to the k. This part is, this is 4 So this is 4 plus k factorial divided by 4 factorial times k factorial. And you see this 4 factorial cancels that. All right. Now we will compute and look at the coefficient of un minus 2. So this part I am erasing. All right. We are trying to get the coefficient of un minus 2. But you see, this is an infinite series in u, and it is multiplied by term 1 minus u. So to get to un minus 2, if you are multiplying with 1, k has to be n minus 2. If you are multiplying with minus u, k has to be n minus 3. So we will keep that in mind. Equals, but I'm pulling from here. That is 2 to the 5 over n plus 1 to the 5. Now for the first term, 1, k is n minus 2. So it is n plus 2 factorial divided by n minus 2 factorial. So let me write here as I did before. For the one term, we will take k equals n minus 2. When multiplies with minus u, where is it? It's here. K will be n minus 3. Okay? So when k is n minus 2, 4 plus n minus 2, that's n plus 2 factorial divided by n minus 2 factorial times n minus 1 over n plus 1 to the power n minus 2. Next, I am multiplying by minus u. So I will take one less power from here. That will be n minus 3. So if it's n minus 3, 4 plus n minus 3. So it is n plus 1 factorial. Sign is minus. N plus 1 factorial divided by n minus 3 factorial. K is n minus 3 factorial times n minus 1, n plus 1, n minus 3. This is multiplied by un minus 2, and I have other powers, but I need the coefficient of this one. Okay, I don't care about the others. So we will do some work with here. 2 to the 5, n plus 1 to the 5. So this is contained in here, so I take it out, and this is also contained in here. So n plus 1 factorial divided by n minus 3 factorial times n minus 1 over n plus 1 n minus 3 parentheses. Here I have n plus 2. And here I have n minus 2. Here I have n minus 1 over n plus 1, and it is minus 1. So what's this? This is n square minus n plus 2n minus 2 minus this one, n square plus n minus 2n minus 2 divided by n minus 2 n plus 1. equals n squares cancel, minus 2, and this is plus 2, these cancel. Here I have plus n, minus n, so I have only 2n. 2n over n minus 2, n plus 1. So that's it. This is equal to 2 to the 5 times 2. Now I have it 2 to the 6. I have n plus 1 to the 5, and I'm using n plus 1. So I have n plus 6, n plus 1 to the power 6. I'm using this, and I have n minus 2 factorial. Here I have n plus 1 factorial. I did not use the n here, I used the 2. N is waiting, and here it is n minus 1 over n plus 1, n minus 3. I can erase this part now because we did the calculation. This is n plus 1 factorial is n plus 1, n. I used, let me write n here. All right, this is n plus 1, n minus 1 times n minus 2 factorial. So this is 2 to the 6 n square. One n from here, one n when we write it as n plus 1, n minus 1. All right, n plus 1 n plus 1 over 6. This is gone. N minus 1 to n minus 2 over n plus 1 to n minus 3 equals 2 to the 6 n square n minus 1 n minus 2 over n plus 1. Let's look at the power n minus 3. We are looking at the bottom. Minus 1 plus 6. So it is n plus 1, n plus 2. We are finished. That's it. So what did we find? We found Jn minus 2. So I will simply write it there. Okay. Now, I will erase this part because we don't need it. I only need this result, so I'm erasing everybody else. But first let me write it. This is equal to n over 2, 5 times 2 to the 6 square n minus 1 n minus 2 over n plus 1 n plus 2. Okay, I'm erasing all the rest. Now we have the normalization coefficients. We will put them in. So N1 and 2R, this is the dynamical coupling through the electric dipole operator, is equal to 4 over n7 root n plus 1 n minus 1, and then I have another 2 I wrote the normalization constants. Then I have n over 2, 5, 2 to the 6, n square, n minus 1, n minus 2 over n plus 1, n plus 2 equals powers of 2. This is power is 2, 1, 3, 9 minus 5 is 4, 2 to the 4. Then powers of n, 5 plus 2, 7, and downstairs 7.5, so it is n 7.5. Then n minus 1. I have n minus 2. We have to subtract another 1/2. So this is 4 over 2 plus 1 over 2, 5 over 2. So it is n minus 5 over 2 divided by n plus 1, n plus 2 plus 1/2. 2 plus 1/2 is 5/2. So it is n plus 5/2. Finished. This is our, this is equal to r n1 r 10. This is just the radial integral. Okay. So if you write the full thing, let me write it here. N L M D 100 is equal to minus u over root 3. The angular part, this is delta m minus 1 epsilon plus minus m1 epsilon minus plus delta m 0 epsilon 0 times this thing, 2 to the 4 n 7/2 n minus 1 n minus 5 over 2 over n plus 1 n plus 5 over 2. Okay, so I will erase it. When we, this is the transition amplitude. This is the Lyman transition amplitude. And if we square it, remember, because of the orthonormality of these vectors, simply these Kronecker deltas. And so any m value, whether it's the decay of the extension of the m equals 0 or m equals 1 or minus 1, they couple with the same strength. And this is the dynamical strength factor. I am erasing this part. All right. Let me, of course, insert here delta L1. Namely, otherwise it cannot connect. For example, the 2s state, n equals 2, 0, 0, d1, 0, 0 is of course 0 because of the angular momentum. All right. Okay. Now, I want to discuss the spontaneous emission rate from the n equals 2 level. So, this is n equals 1, L equals 0, and let's take, for a specificity, take n equals 2, or any n, L equals 1, and M could be anything because all of them have the same strength. All right. To compute the spontaneous emission, of course, will take some time, but we can do with some analogy because the results are very similar. And I would like to remind you from classical electromagnetic theory. If you have a dipole, suppose we are approximating a charge distribution with its dipole, and if dipole has this characteristic, if P physical is the real part of P0 e to the minus I omega t, and P0, let us take AQ, this is a unit vector in some direction, and you can even put a phase here, e to the I delta, complex vector. The physical, of course, the real part. So, if this is the n direction, our dipole is flip-flop, is oscillating in this direction. In that case, if the assumption is that, or the physical situation is that, if the charge is non-relativistic, and if the wavelength is very much bigger than the source, then you can make an electric dipole approximation. I am talking about the classical electric dipole radiation. In that case, the average power, this means this is not a vector, this is just the average power radiated in the polarization state sigma per unit solid angle can be written like this: 1 over 4 pi epsilon 0 omega 4 over 8 pi c cubed epsilon sigma dot P0 absolute square. I'm writing it in this fashion because together with 1 over 4 pi epsilon 0, this is in the MKS units. Without 1 over 4 pi epsilon 0, you are in the Gaussian units. So you can use any unit system you want. So this is if it's polarization sigma. You see, the radiation, the classical radiation is like this. Suppose you are looking at an arbitrary direction r. Of course, you are far away from the source, and then the field vectors are in a plane perpendicular to this r. So you can take, if you are looking at an r, you can take the polarization vectors in this plane. Of course, you can use any complete set of vectors, but it's perhaps easier like that. Now, if you want to look at all the, irrespective of polarization, the total power radiated in that angle, irrespective of the polarization, you have to sum over the polarizations. So let's do the sum. Sigma dp sigma d omega is simply dp d omega. That's equal to 1 over 4 pi epsilon 0. That thing, omega 4 over 8 pi c cubed. Then I will write it like this: P0 complex conjugate dot sum over sigma epsilon sigma epsilon sigma. There is no dot here. I'm writing a dyadic. Star dot P0. This is sigma and we are summing over sigma, and this is P0. And this has the, this is, I can call it 1 in the perpendicular direction, or 1 minus RR. Namely, it is the perpendicular component of P0 counts. Perpendicular to R. Of course, you can change the your detector, and R, which depends on the angles, will change. So the result is that this thing is equal to 1 over 4 pi epsilon 0 omega 4 over 8 pi c cubed times P0 perpendicular square. Let me erase this part. And P0 perpendicular square is P0 square minus R dot P0 absolute square. Okay. Where, for example, we took P0 here. Now, this is irrespective of the polarization, the average power radiated in this per unit solid angle in this direction, in the R direction. What is the total power radiated by our dipole? So P is simply omega dp d omega. So this is the only thing that depends on the angles. Okay. So it is 1 over 4 pi epsilon 0 omega 4 over 8 pi c cubed times. Now, if this is n, and if this is r, and if this is the angle between, namely we take n as the polar axis, if you wish, then we have P0 square times the omega sine squared theta. This sine squared theta because it is P0 square minus P0 square. R dot P0 is cosine squared theta. So it is P0 square 1 minus cosine squared theta. That's equal to P0 square sine squared theta. So let us take this integral. And it's easy, we can do it quickly. We have a d phi integral from 0 to 2 pi. Then we have 0 to pi d theta sine theta sine squared theta. This is d cosine theta, so it is d mu. Integral is from, this is minus d mu. This is from 1 to minus 1 for cosine theta. This was minus, so sine flips minus 1 to plus 1. And this is 1 minus cosine squared theta, 1 minus mu square. D phi gives me 2 pi times, this gives me 2, this part, 2 minus 2 over 3. 3 times 2 is 6, minus 2 is 4. 4 times 2 is 8, so it is 8 pi over 3. So the result of this, the average power radiated over all the directions is 1 over 4 pi epsilon 0 omega to the 4th P0 square. 8 pi cancels this over 3c cubed. Okay, so this is the famous classical. All right, we did the, I gave you the radiation to a certain direction of a certain polarization. Then total radiation, we sum over the polarizations, it is this. And overall directions, we integrate over the angles, and this is the result. This is the classical theory. The question is, what's the quantum counterpart? Of course, the quantum counterpart, you cannot just take, here I have P0, I replace it by dipole. You have to go through the whole machinery of time-dependent perturbation theory. You introduce the electromagnetic field, work it out. Now, it's a bit long calculation. Except the result is so simple and so similar, we can immediately do it. So I will simply write the result. I'm erasing here. And since all m's are equivalent, let me just take all m's are equivalent. Let me just take one m. Let me just take n10 d. I want to erase this part, you can imagine. 100 equals minus e over root 3. I already put L equals 1, so this is there. I'm just taking this one, delta m. I'm taking the m equals 0 state, so it is epsilon 0. That's our dipole in the z direction times 2 to the 4. All these chokes keep breaking. 2 to the 4 and 7/2 and minus 1 and minus 5 over 2 divided by n plus 1 and plus 5 over 2. That's it. Now I'm erasing the here. I will write by analogy. By analogy, because we do the time-dependent perturbation theory, and the perturbing thing is the electromagnetic field, etc. But the end result is almost identical, so we can just do it. As I say, the justification is doing that calculation, not through here. But if you do that, the result of that fully quantum mechanical calculation is this. First, D is, since we are computing energies and all that, D is R, proportional to R, and R is the physical distance. So when I say D physical, that means I am using R physical. Remember, our R's, etc., were without dimension. Now I introduce dimension. It is R times A0. So I put here an A0. That's the Bohr radius, basically. Okay, we had scaled it radius in that fashion. Now, analogy goes like this: replace P by 2D, 2D I to F. Here, this is I, the initial state, and it is decaying to the ground state, which is the final state. So we are finished. Let me just copy these formulas. I will not write time average. I will just say dp sigma atomic over d omega per unit solid angle is 1 over 4 pi epsilon 0 omega to the 4. Replace P0 by 2D, so it is 4 over 8 pi C cubed times epsilon sigma dot di f. Of course, I'm using physical with A0. dp, if I sum over polarizations, it just picks up the perpendicular component of d vector to the direction of observation. So it is equal to 1 over 4 pi epsilon 0 for omega 4 over 8 pi c cubed d I to f perpendicular square. And if you integrate this over, okay, instead of n there, here I have epsilon 0, the direction of the dipole. So you take the direction of r and epsilon 0, which is the z-axis, that's theta. So it's the same result. P bar is equal to 1 over 4 pi epsilon 0 for omega 4 d I to f physical square divided by 8 pi c cubed, but we are multiplying by 8 pi over 3 because we are making the angular integration. So 8 pi is gone, 8 pi over 3, so you have 3 c cubed. Remember, this will involve the physical, which will have a0 square. So we will go from here. I will erase the rest. Again, this prescription of if dipole is given like this, p physical is like this, and the prescription here, you cannot do it blindly. You must first do a fully quantum mechanical thing, which will take quite a bit of time. I skip, but the results are almost identical, simply replacing by p by 2d. So I think so this is I will operate on, this is I will discuss. I am erasing all the rest. All the discussion about the classical electric dipole radiation. I'm erasing. And we don't need radiation in, with certain polarization. I'm erasing that also. So we have seen that in classical electrodynamics, an accelerating charge or system radiates, and under certain conditions that the wavelength is larger than the source region, velocities are non-relativistic, we have an electric dipole radiation. So the quantum counterpart of the accelerating and radiating charge, that radiation, is spontaneous emission. That's the quantum counterpart of classically radiating accelerating particle. All right. So power here, power. This is the power radiated. This is energy per unit time. So I can write this thing as 1 over time times the energy. Energy of the outgoing photon. Okay. So this is h bar omega, and this I will call A, the spontaneous transition rate from n to 1 in this case. Okay. And E of t is just what we found there. So let's write. This is 1 over 4 pi epsilon 0 times 4 omega 4 d physical I to f square over 3c cubed. This is just the power, E of t. That's equal to A times h bar omega. This is the Einstein coefficient of spontaneous emission. So A is equal to, one of the omegas cancel. So it is 1 over 4 pi epsilon 0 for omega 4 over omega 3. 3 h bar c cubed d physical square. What's that? And I'm taking this n 1 0, let's say, going to 1 0 0 times d square. Well, I have an a0 square times e square over 3, 2 to the 8 n to the 7, n minus 1, 2n minus 5 divided by n plus 1, 2n plus 5. Okay, so this is the Einstein's A coefficient for level n, L equals 1, m equals 0, 1, 0, 0. Because the strength of all the m values were the same, it's the same for all the m's. So that's it. This is the formula. Lyman, spontaneous emission. Okay, now I will erase the rest, and we shall get a feel about the numerical value of A for Lyman Alpha transition. Alpha is from n equals 1. This is n equals 2. Any m value would do. We just took m equals 0, but they're all the same. A. So this transition rate is A. So let us numerically compute this thing. I'm erasing all the rest. Okay, so let us estimate A for Lyman alpha transition. We mean this. We will compute that. So n equals 2. So A 2 1 0 going to 1 0 0. Now let's see what we have here. E square over 4 pi epsilon 0. E square over 4 pi epsilon 0 divided by I take an h bar c here, h bar c. So that's one combination. Next, I have 4 over 3. So this is gone, this is gone. 4 over 3. Let me multiply by h omega h cube, and here let me just divide by h cubed. Let me write hc cubed, but I used 1c for there, so I will multiply this by c, and then I have a0 square. All right, where am I? I'm here. Then I have 1 over 3. I'm here. Now I'll put n equals 2. So n equals 2. 2 to the 7, this is 2 to the 15. 2, 15. 2 minus 1 is 1, so it is 1 to the integer power, that's 1. Then I have 2 here, 3 divided by 3. 2 times 2 is 4, n equals 2. 5, 10. No, 9. Let me look at this. And A0 square is, let me write it here, it is 1 over 4 angstrom square. And let me write C here. 3 times 10 to the 8 meters per second, since we have angstroms, times 10 to the 10 angstrom per second. All right. I have a 3 over 4, 4 over 3, so they are gone. Let me look at this factor. I can write this thing as 1 over 2, 2 to the 16, and this is 3 to the 10. So it is 2 to the 8 over 3 to the 5 square. Well, this is an interesting number. 2 to the 8, that's equal to 1 over 2. 2 to the 4 is 16. 16 times 16 is 256. 256. 3 to the 5. 3 square is 9. 9 times 9 is 81. 3 times 81 is 243. 243 square. One cannot help but notice that this is the semitone of the Pythagorean musical scale. So, as Pythagorean, that's the semitone of the Pythagorean musical scale. This is 256 over 243. Because their Pythagorean is perfect 4 divided by whole tones square. So perfect 4 is 4 over 3. This is 9 over 8 times 9 over 8. That's equal to 8 times 8 is 64. 4 times 64 is 256. Divided by, again, 3 to the 5 here. That's 243. All right. I don't want to make something out of it, but it's not something that you can run into often. It's funny that it comes out here. All right. So let's continue. Equals. Let's put in some the numbers now. This is fine structure constant. Fine structure constant, and that's 137. It has no units, so it's 1 over 137. This one, h omega, this is at 3.4. This is at minus 3.4. This is at minus 13.6. So this is 10.2 cubed electron volts cubed. That's it. Divided by, this is 2000 electron volt angstrom. So it is 2 to the cubed, and 1000 to the cube is 10 to the 9 electron volt cube angstrom to the cube. Where am I? I am here. Then I have 1 over 2 times Pythagorean semitone square. Then I have 10 to the 8, 10 to the 28, 10 to the 18, not 28. So these are the numbers. Let me just put it. So this is 1 over 137, let's say 140. So it is 1.4. And this is 16, 1.6. I took 10 here, 100 here, times 10 to the cubed. And then 10 to the 9. Electron volt cubes cancelled. I had angstrom cubed here, so angstrom cubed, so they cancel. So I only have 1 over second as the proper unit of the transition length. So I will simply call this 1 square. I will replace this one. Remember, we are making an approximate calculation. 10 to the 9. And this is 10 to the cubed. And 10 to the 18. Equals. So this cancels. This gives me 9. All right. What is this? This is a bit bigger than 1.5. This is a bit smaller than 1.5. Square is 2.2. Call it something like 2, roughly speaking. 1 over 2. So it is 1 over 2, 10 to the 9, 1 over second. We are finished. It says that transition rate, spontaneous emission rate is 1/2 10 to the 9 seconds. And the lifetime of the state, is defined to be 1 over A. This is tau. Tau equals 1 over A. And this is 2 times 10 to the minus seconds. So the n equals 2 state lives about 10 to the 2 times 2 nanoseconds. It's a nanosecond, 2 nanoseconds, and it decays. All right, and of course, this is the spontaneous emission. What did we do? We computed the transition matrix element. Here we use the physical R, so we multiply by the scale factor R A0. And we use the result that the fully quantum mechanical result is the same thing as the classical result. But if you make this replacement, this is the general formula. And for the particular case of Lyman Alpha transition, this is the rate. And what does lifetime mean? Lifetime is this. N of t is n of 0. Suppose at time 0 you have so many hydrogen atoms in the n equals 2 state, m equals 0. It is e to the minus t over tau. Tau is lifetime. It's not the half-life, but it is, of course, related to that. just to mention it, and T1/2 is 1/2 n0. That's equal to n0 e to the minus t over tau. So you cancel the n0s, take the log T1/2. So T1/2 is tau times log 2. But for us, they're about the same. This is 0.7. They're about the same. All right, so this is the spontaneous emission. If you wonder what are the, once you have A, of course, once we have the A coefficient, we have the B coefficients. So A over R, this is the rate, this is either the simulated emission or the absorption rate. So it goes as e to the h bar omega over kBt minus 1. So once we have the A coefficient, Einstein's A coefficient, you have the Einstein's B coefficient also. The formula is given in every book, so I will not repeat it. So if you multiply the B coefficient with the density, you get this rate, and the ratio is simply that. All right. I want to mention last astrophysical application of the Lyman Alpha transition. So astrophysics. We are doing Lyman Alpha transitions from n equals 2 to n equals 1. And so when we have n equals 1 and n equals 2, all right, we have a spontaneous emission from n equals 2 to n equals 1. There is a simulated emission, that's the B coefficient of Einstein, and there is the absorption from here to there. All right, now there is an interesting astrophysical application of this. Suppose here there is a quasar, and here is Earth, and here is our detectors, and we are detecting the radiation coming from the quasar. Quasars are very distant and very powerful energy sources, and they radiate basically in a broad range of frequencies. So if we plot, for example, here is the flux, how many photons we are getting per second to this detector, and if we plot here the lambda. So quasar is emitting in a broad range of frequencies, but there is one frequency that will have a peak because there is a lot of hydrogen, and this hydrogen is excited to n equals 2. Then it decays by a spontaneous emission and also by simulated emission. So instead of getting a uniform flux from all lambdas, we have a big bump emission. But of course, this will be Lyman transitions go from to 9, what did we find? Something like 9/11. I don't want to call 9/11s. Let me call it, what did we do? 9/20. 9/11 something. Reminds something bad. Okay, so let's say 9/20. So this is the alpha wavelength. But so if we were just near the quasar, we would have measured lambda to be 1000 to 16 angstroms. But of course, this is now several thousand. Why? Because by the time light reaches us, the universe has expanded. And so this is several, depending on, of course, which quasar you look at, several thousand. Okay, that's the emission. Now, between us and the quasar, there would be a big cloud of hydrogen. So this cloud of hydrogen will absorb the radiation and will get excited to the n equals 2 level. So there, because it's absorbed, there will be a dip in the flux. So this will be the absorption. All right. Now, however, the picture is more complicated than this. Why? Because we don't have a single cloud of hydrogen between the quasar and us. There are several. So this is hydrogen cloud 1, then hydrogen cloud 2, and this is hydrogen, let's say cloud n. So there are these hydrogen clouds. So you get absorption for these. So you can, this will be cloud, for cloud 1, we will have lambda 1, we will have lambda 2, we have lambda 3. Why is this and that lambda bigger than these? Okay. It is because they are further away, and by the time they get to us, the universe has expanded more for this photon than this photon. So they will have shorter wavelengths, and these will have longer wavelengths. So this is called the Lyman Alpha forest, because there are many of these. What do we hope to learn from this? First, we learned that hydrogen exists in the universe in lumps. It's not a uniform distribution. It exists in lumps. So then one wonders, so this is neutral hydrogen. Neutral hydrogen is absorbing the radiation and going to here, and then this is decaying, but you get these absorption dips. Neutral hydrogen, okay, exists in lumps. It's not a uniform distribution, as one might perhaps guess at the beginning. Then you say, why is that? Why is it in lumps? It is because matter provides an attraction, gravity, and most of the matter is what we call the dark matter. So if there is a potential valve of dark matter, hydrogen will be attracted to that. Dark matter will attract. Therefore, by looking at these neutral hydrogen lumps, which you can detect by these absorption dips or the Lyman Alpha forest analysis, you can, astrophysicists hope to obtain the distribution of dark matter in the universe, to map the dark matter. And there are other things that you may learn from Lyman Alpha forest. Okay, let me just summarize in a few words. We looked at the dipole radiation, and so we looked at the dipole radiation. from levels n larger than 2 to n equals 1 to ground state. These are the Lyman. This radiation is in ultraviolet, and we computed the matrix element, dipole matrix element, and we have seen that the lifetime of the Lyman alpha state, namely n equals 2, is 2 times 2 nanoseconds. That's tau. Okay, and well, we computed the coupling matrix element, the transition matrix element, and we have seen an astrophysical application of that. Thank you.